Warm greetings, everyone. Welcome to the session by Initiatives for Girls in Physics (IZP) on particle physics at LHC. IZP is a young female STEM enthusiast led community having a vision to empower young girls in physics and other STEM fields linked with it, providing them the platform to learn, share, and connect. The IZP family wishes you all a very happy International Women's Day. In this session, you will get to hear from Dr.Thea Klaeboe Aarrestad, a particle physicist and a senior research fellow at CERN, about the basic functioning of LHC, Large Hadron Collider, as well as her journey in the field of physics.
So again, hi everyone. Thank you very much for having me here. I'm really honored to be the first speaker for the Initiative for Girls in Physics. It's really a case very close to my heart, as I've been in physics very long and there's always been very few females comparatively. So I think this is absolutely great, and I'm really excited to see where you go with this organization. It's really great. So as you've already said, I'm a particle physicist. I'm currently working at CERN, where I do particle physics, but also a lot of computer science, AI, etc. So today I'll be talking mostly about particle physics, more specifically particles and fields at the Large Hadron Collider. So I'll talk a little bit about particle physics in general, and I'll also talk a little bit about how we do particle physics at LHC and what the future of particle physics is. So first and foremost, before I begin, I just wanted to quickly introduce myself, since this is kind of an informal session. So hi, everyone. I don't know if you still see my face. I'm Thea. I'm currently in Zurich in Switzerland, but I'm originally from Norway, from Bergen in Norway. And my academic career started there. So I started with a bachelor in physics in Norway at the University of Bergen. This is a nice picture of Bergen where you can see it's surrounded by these high mountains. There's always a lot of snow in winter, and we have all these colorful houses everywhere. So when I was a bachelor student, I focused a lot on astrophysics. I was really interested in cosmology, astroparticle physics, the origins of the universe, etc. But I also started slowly getting very interested in particle physics, because once you start asking yourself big questions about the universe, you realize that the big questions about the universe can be answered at the smallest possible scales. So that really got me excited. And also we have a technician from Nepal in the University of Bergen CERN group. So the world is really, really small. He's been there for a couple of years now. And if you're interested in hearing more about what he does, I can absolutely try to get you in touch. But so being at the University of Bergen and learning about particle physics, I realized that's what I want to do. That's like the real way we can answer questions about our universe. So I looked around in Europe where I could do more particle physics and learn from the best and kind of get a broader idea of everything. And I found ETH Zurich, which is a great school in the natural sciences. They have a lot of classes in particle physics. It's a really international community, so there's a lot of exchange students and a very good environment. So I moved to Zurich in 2012, first as an exchange student, and then I eventually ended up liking it so much that I also did my master's at ETH Zurich and then a PhD at the University of Zurich. And here you can see the physics campus in Zurich. And so here I started really getting into particle physics and realized that that's what I want to spend my career on researching. But at the same time, I applied for something that's called a CERN summer student program. So CERN accepts students every year from all countries to their summer student program. So you can come and do a project with other researchers, learn about particle physics. Here you can see the whole CMS collaboration in 2012, where I was part. And up until now, we've had 7 CERN summer students coming from Nepal. So there's also a possibility when you're doing your undergrads that you can come to CERN as a summer student. And I really recommend everyone to do that. So when I finished my PhD, I wanted to stay at CERN because it's an amazing place if you want to learn fundamental science. So I got a position as a senior research fellow there. And here you can see a picture of me together with two researchers from Google. I'm also a guide, so I'm allowed to take people underground to see the particle detectors, which are 100 meters underground. And here, as a senior researcher, I've gotten really interested in machine learning and artificial intelligence and how we can use machine learning to improve the physics that we're doing. And also at CERN, I have a few colleagues from Nepal. There are very few, so we currently have 4 researchers from Nepal, some theoretical physicists, some experimental physicists, and also science communicators. And so there's a small but growing community of Nepalese at CERN. Okay, so that was sort of the personal introduction. Now I want to take you to my office and what we do. So this is where I work, almost. This is the Large Hadron Collider. The Large Hadron Collider is the largest particle accelerator ever built by mankind, and it can accelerate particles to unprecedented speeds and energies. So it's located at the border between Switzerland, which is here, and France, which is here. And it's a 27-kilometer long ring. It's huge, and it's located 100 meters underground. So it's absolutely massive. And the purpose of this ring is to accelerate little particles we call protons, which you see here. We make them go faster and faster and faster and faster, up to 99.9999991% the speed of light. So they're really, really fast. And then we smash them together as hard as we can to see what comes out of the collision, to study the smallest pieces of the universe. So the very first thing I wanted to do was to take you on a tour of the LHC. How do we go from, how do we produce these protons? How do we accelerate them? How do we smash them into each other? So all the magic starts at a little tiny tank, which is located here. I hope you see my mouse, right here. That's the very beginning. And now let's go into the machinery. So this is where the journey of a proton starts. We have a tiny tank of hydrogen, which is located at the very beginning of the LHC. It has high pressure, so the hydrogen is pushed out of this bottle and into a chamber. Now, hydrogen contains of a bound state of a proton and an electron. What we have to do is we have to strip the electron away because we only want the proton. So in this chamber, we take the blue electrons, we keep them back, and we only allow the red ones, the protons, to pass through and go into the accelerator complex itself. So that's how we generate this beam of protons. We have this tiny, it's probably this big, this little hydrogen tank, and it's what feeds this whole 27-kilometer ring. When the protons come out of this chamber, they're pretty slow. We want them to be faster. We want them to have more energy so that the collision itself has more energy. So what we have to do next is accelerate them. So now we were here, we produce the protons and we want to shoot them into the LHC complex. So the first thing that happens is that the protons enter what's called the LINAC, a linear accelerator. And it's built on something called radio frequency cavities. So these protons, they're charged. So when they enter this RF cavities, the first thing they will see is an electric field, and the electric field will attract the protons, and then it will reject it on the other side. So first it will see an attractive potential, and when it passes through, the electric field will switch and it will see a repulsive potential. So it gets attracted and repulsed, attracted and repulsed, attracted, repulsed. And we switch these fields ultra fast so that it always sees a potential that pushes it along. And using that technology, we can make the particles go faster and faster and faster. Now, once the particle reaches the end of the LINAC, they're only a little bit faster than what they were to begin with, not at all as fast as we need them to be. So we need to go to 3 more steps before they're fast enough for injection in the LHC. So just to give you an idea of how big this beam is, here you can see the beam size. So this is now a bunch of protons, which is roughly thickness of the hair wide, so 2 millimeters. If you have a €1 coin, it would fit through Spain on that coin. So it's really thin, and it's just a few centimeters long. And in that little bunch of protons, we have hundreds of billions of little protons in this a tiny, tiny packet. So this tiny packet of protons then needs to be accelerated further. So the first thing we do is send it into what we call the booster. And in this booster, they go around and around and around, and we have all these RF cavities in there that always push them along and keeps them in these tiny little bunches and pushes them faster and faster and faster and faster. And here you can see what it looks like. They have these 4 pipes, so we can keep a lot of protons in this booster at the same time. So that gets them up to even higher energies, but it's still not enough. So after they've been in this booster, they need to go into another chamber that we call the proton synchrotron. They go from this booster into the proton synchrotron, where they're again kicked along and kept in tiny packets. Then they go into the super proton synchrotron, which is a huge particle accelerator. It's 7 kilometers long. And there they get the final little push they need to get fast enough to enter into the LHC. So now they will have an energy of 450 giga electron volts, we call it. And at the end in LHC, they will have an energy which is 1,000 times that of which it gets from the SPS. Okay, so now comes the really exciting part. Now we have these bunches of protons in the SPS, and we have to push them into the Large Hadron Collider. So we need to bunch them in these little small packets. Each packet of proton is 25 nanoseconds from the other packet. So there's always a little gap in between each bunch of particles. Then we inject them into the LHC, one beam, one direction, another beam, the other direction. And we make them go around and around and around and make them go faster and faster and faster in opposite direction. And here you can see what it looks like, the 2 beams passing each other at almost the speed of light in this tiny, tiny beam pipe. So you see here, there are these 2 pipes there with one beam going one way and the other beam going the other way. So the next step now is to do what we intended to do. We need to smash them together. So all along this ring, we have these beams of particles that go around and around and around. Then we have these cameras all around the ring, because when we smash those protons together, we want to see what comes out. We need to take a picture of the collision of what happens. So we have a particle detector called ALICE, one called ATLAS, one called LHCb, and one called CMS. And here you can see a picture of CMS. That's the experiment I work for, where you see this tiny thing in the middle is the beam pipe where the protons are brought to collide. And this huge apparatus, 15,000 tons, 15 meters high, it's absolutely huge, is all instruments used to detect what comes out when we smash those protons together. So what happens next is that the 2 beams have their final speed, a fraction of the speed of light. Now we need to collimate them, squeeze them together as tightly as we can, those bunches of protons, and then crash them together. We bend them and then smash them together in the center of the detector. And what happens then is that they collide, they smash, and a bunch of other particles come out, just a huge spray of outgoing particles. And this happens every 25 nanoseconds. There's a new such collision that we measure with our detectors. So this is what it looks like in the event. This is now a real event display. This is what I look like every day at work. I've had the protons coming in here, then they collide in the center of the detector. But now you might ask yourself, that's kind of strange. So I have 2 protons that come in and then a bunch of things coming out. Why is that? Are we looking at what's inside the proton? Some people use this analogy that you take 2 Swiss watches, you smash them together as hard as you can, just to see what's inside them, to see what comes out. But this is absolutely not what happens in particle physics. So where are the protons actually? What actually happens is that the protons come in, they completely vanish, and they turn into a bunch of new particles that weren't there before. So apparently this simplified picture that we always tell people, which is, okay, we have protons, we accelerate them, we smash them together, and we see what comes out. There's a lot of questions related to that. First of all, where are the protons? Second of all, where do these other things come from? How did we invent those? Where do they come from? So we need to go a little bit deeper into the details to understand particle physics. So probably, I don't know what your previous experience are, but usually up until 1964, when we thought about protons, we thought of them as elementary particles. Protons was just some ball, the smallest thing you could have. But then something happened. We started to see a bunch of new particles that were kind of similar to protons, but a little bit heavier. And we found more and more and more and more and more of those things. And we didn't really understand where they came from. So Murray Gell-Mann said, hey, what if the proton isn't really elementary, but it consists of something smaller? It has these elementary particles within it, which are called quarks. It has 3 quarks. It has an up quark, 2 up quarks, the red ones, and a down quark. And these quarks, they're buzzing around at the speed of light inside this proton, but they're only held together by a force. And this force we call gluons, and that's what glues these protons together. So it's not really at all a ball, an elementary ball. It's actually a bound state of 3 quarks bound together by gluons. And most of the things inside the protons is just air, and the quarks are really light. So what makes the proton so heavy is this interaction, this strong interaction that makes the proton so heavy. So that gives us a different picture of what actually happens at the LHC. So what actually happens is that we're accelerating bound states of quarks that you see here, hold together by gluons. And when they meet in the detector, it's not really the 2 protons that are brought together to collide. It's the tiny little quarks inside the protons that we carefully need to make collide. And like I said, this is mostly air inside those protons. So getting them to hit each other is really improbable, which is why we have hundreds of billions of protons in each bunch with the hope that some will collide. And when they do collide, what happens is that they completely vanish. All their energy is turned into the mass of some new particle. They're gone forever. And then this new particle, which is generated out of nothing, can then decay, for instance, into other particles. It can turn into other particles that we can measure in our detectors. But there's still an unanswered question here, because we just answered the question, what happens to the protons? We discovered actually they're not protons that collide, it's quarks that collide. And those quarks, they collide and then they vanish. How does that happen? So there's been a big misconception with what I do. I said, and people say, and on my CV it says that I'm a particle physicist. And we think of particles as the smallest fundamental constituent of matter. But this is not true. We've come to understand that the smallest constituent of matter isn't particles at all, but they're fields. More precisely, they're quantum fields. So instead of having little tiny balls, a quark in the universe, what I have is a quark field, a huge field that has a value everywhere in space and everywhere in time. So what we before thought of as a quark is now a field spread out through space and time. And you can think of this as temperature. So temperature is a field. Every point in space has a temperature, it has a value. So it's a temperature field. In the same way, you can have a quark field. But how do we see things that look like particle? Well, that's because of something we call an excitation of the field. So if you have a field and you put enough energy into that field, you can wiggle it just enough to make a little wave, a ripple. And this wave or ripple, it will look like a particle. So every time we put a bunch of energy into a field, we make a tiny little ripple in it. And that tiny little ripple, this bump here, is what we observe and think of as a particle. So a particle itself is just an excitation of the underlying field. So that's the reason why you can have 2 quarks coming in, all of their energy, they smash together, and all of that energy is used to make a wave in the field of some other particle. And this little wave will look like a particle. So that's how we can explain that things come out of nothing, come out of the vacuum. So if you think fields sound kind of abstract, they're not really. I mean, we've all held magnets in our hands, bar magnets, and felt this force between them when we bring them together. We don't see anything, but the reason this happens is because there is a force field. There's an electromagnetic field, and this field makes you feel that there's some resistance because it's sending little photons between each other. And here you can see the field lines of a magnet. So if you have magnetic dust and you hold a magnet close to it, it will look something like this. So it's a really natural thought when you think of it. So that sort of explains the following. You have the two quarks coming in. We accelerate them because we need them to have high energy, and they have kinetic energy. Kinetic energy is mass times velocity squared. So the higher the velocity, the more we accelerate them, the more energy they will have. And we can use that energy here of those quarks to generate mass. E equals mc squared, remember. So we generate a mass, we generate new particles, which is then all these lines and red and blue things that we measure in the detector that you can see on this picture. So that's the story about particle physics. There's not really particles, but fields. And what are those fields? So these are the fields we had in 2012. You'll understand why I am showing you only those fields for now. So our picture was the following. We had quarks, which are the up quark, the down quark. If you remember, those are the things that build up the proton, up quarks and down quarks. Then they have heavier siblings, which we call charm and strange and top and bottom. And we have no clue why those siblings exist. They're exactly the same as up and down, just a little bit heavier. Then we also have leptons, which are down here, the electron you all know. So for instance, an atom just consists of these up and down quarks inside a proton, and then an electron that goes around it. So all the matter around us, my computer, me, the table, your computer, it's basically made by up quarks, down quarks, electrons, and then the forces, so gluons. And so the force carriers is what makes these things talk to each other. So again, if you think of the picture of the proton, you have the up quarks and the down quarks, and they talk to each other, exchanging particles called gluon. They bounce them back and forth, and this back and forth bouncing is what makes them talk to each other. Then we have the mediator of the electromagnetic force, photon, which you're all familiar with, which is basically the rainbow you see, why the sky is blue, all these sorts of things. Then we also have the mediators of the weak force, the Z boson and the W boson. So these are all the fields we have, and all of those fields also come with the particles. The things listed here are the particles we should see. Now, we have this clear idea of the particles and forces of nature, but there was one thing, I'm sorry, but a person is drawing on my screen. Maybe if you could make sure you can't do that. Thank you very much. Okay, so there was one thing we couldn't really explain. In our first theory, these particles had no mass. So the quarks had no mass, the force carriers had no mass, the leptons had no mass. But then when we measured them in experiments, they had a mass, which our model couldn't explain. So for instance, the lightest particles, the neutrinos down here, they're really, really light. It's these guys here. They have a mass less than 1 eV, we call it. Then the heaviest particle, the top quark, is super heavy, in order of billions heavier than the neutrinos. It's all the way up here. That's this top quark here, which is the heaviest particle we have. And we had no way of understanding why these particles have mass. So that was a huge mystery, and it was a huge fault in the standard model of particle physics. So in 1966, there were a lot of people that thought a lot about this, because we had measured that particles have mass, but they weren't supposed to. So a bunch of brilliant physicists, more specifically Brout, Englert, and Higgs, which got the Nobel Prize in 2013, invented something which is called the BEH mechanism, or you've probably heard about it as the Higgs mechanism, but actually these people invented it at the same time. So the Higgs mechanism attempts to explain why particles get their mass and what is the mechanism of which gives particles their mass. And then there was a prediction from a scientist called Peter Higgs that said, okay, if this mechanism exists, there needs to be a quantum field, the Higgs field, and this quantum Higgs field leads to a Higgs boson. If we wiggle that field, we should see a particle, and that particle is the Higgs boson. So that's the story. Then what is actually the Higgs mechanism, and what does give particles their mass? So in order to understand that, we have to go back to the very, 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 very early universe, when the universe was just a fraction of the size. It was so small we cannot even imagine it. So then all the particles existed together, and they were all massless. They were all whooshing around, the top quark, the Higgs quark, the W boson, the Z bosons. All the particles have no mass. And they were just whooshing around as they wanted, with nothing stopping them. The photon still has no mass and is still whooshing around at the speed of light. So as the universe expanded, they kept whooshing around completely unstopped. But at some point, something very strange happened, and it's similar to frost on your window. A field, something called the Higgs field, suddenly appeared, and it sort of manifested itself throughout the universe. And it's like a temperature field. It has just a value at every single point. And the effect of this field and particle physics is huge. So before, we had these particles that could whoosh around as they want. They were massless like the photon. They were just flying around, nothing there to stop them. But the Higgs field did something to some of them. Some could pass through it like before, they didn't care. But some were a little bit slowed down by the Higgs field. Some were slowed down more. And for instance, the top quark was slowed down by a lot. These are all top quarks going through the Higgs field. So they appear to have a mass. Their kinetic energy, the mc squared, is turned into another form of energy that we call mass. So mass is just this really concentrated form of energy, and it's related to E equals mc squared. And a particle can either have more energy or more mass, depending on the particle. So let's look at some of the particles that we have in the standard model. So for instance, the electron has most of its energy in kinetic energy. It's really light. The muon is heavier. It has less kinetic energy. And the top quark has all its energy in mass and almost nothing as energy. So that's sort of what explained why all these particles were now suddenly appearing to be heavier. But what actually happens in this field? How do we think of it? Well, what we think of is that this Higgs field has a bunch of Higgs particles that always come in and out of existence. They're kind of vibrating and cooking in this field. So there's a bunch of them just interacting and talking to particles, and we call them virtual particles. They appear and disappear and appear and disappear. They're like a simmering soup. Now, when some particle comes in, let's say it's an electron, it sees this simmering soup and it doesn't care so much. It's slippery. It goes right through it. It doesn't interact so much with anything. So it's light. It doesn't have mass. A muon, on the other hand, is not so slippery. It has more friction. It talks to the Higgs boson more. It's more slowed down. Then you have the W boson, talks even more to it. You see it's like really sticks to it. It has a higher mass, we call it. And then our heaviest particle, the top quark, just gets completely stuck in this thing. It can hardly move. All the kinetic energy it had is now turned into mass. And that's how we think about the Higgs mechanism and the Higgs bosons as a field. So what happened was that we knew there had to be this Higgs field, because otherwise our particles should be massless. So since 1966, we've been thinking about this thing. We've been thinking there needs to be the Higgs field. There needs to be the Higgs field. And we also know the Higgs field means there's a Higgs boson. So the thought was that if there's a Higgs field, the quarks should be able to collide and ripple it out of the vacuum, exactly as we've seen before. Then the Higgs decays into 2 standard model particles. So let me quickly play that for you again. You have again the quarks colliding. They wiggle the Higgs fields. The Higgs field comes into existence, and the Higgs field then decays into particles we can see. That's what the theory predicts. So the LHC was essentially built to find this boson we said had to exist because it had to give particles mass, and we've known about it since 1966. We also had ideas what would happen if the quarks collide. They have a lot of energy. They collide together. The energy ripples the Higgs field. The Higgs comes into existence. And our theory said that the Higgs would then decay. It would then disappear and turn into 2 other particles. That's just how quantum field theory works. And it would look something like this. You would have a Higgs created, which then decays into some other particles that we could see. So we spent years and billions of euros building the largest particle accelerator ever built to find this thing. But how do we find it with a particle detector? So that's why we need to know a little bit more about what the particle detectors consist of. So these are all the particles we could detect. It's the quarks, the leptons, the force carriers. And here you can see a slice of the CMS detector. So now you can think here in the middle, you have the quarks colliding, and then you cut the detector in half and you look kind of radially outwards. This is what it will look like. So this thing goes all the way around the particle, all the way around. So the first thing any particle that's produced will meet is something called the silicon tracker. It's mostly consists of silicon pixel or silicon strips, and it can measure any particle that has some sort of charge, like the electron is negatively charged, so it should leave a signature in the tracker. Then we have an electromagnetic calorimeter. In this thing, the electrons and the photons, they should be stopped here and leave all their energy here so we can measure them. Then we have the hadron calorimeter here, which measures bound states of quarks that we call hadrons. So they leave all their energy here. Then we have the largest magnet ever built. It has the largest magnetic field, at least on Earth, 4 Tesla. And it's really, really huge. And what it does is that if there's a charged particle, the magnetic field will bend that charged particle. And we can see if it's positively charged or negatively charged. And we can estimate its energy from how much it bends. Then all the way out, we have muon chambers used to detect muons. So that was a little bit fast. I just quickly wanted to show you what it looks like when a particle goes through. So for instance, if we have a muon, the heavier cousin of the electron, the muon is so heavy that it will go through our entire detector. It will be made here in the middle from 2 quarks vanishing and rippling the muon field, let's say, or something else. And then it will travel through the whole detector, and you can see that it's curved, right? It has this S shape. That's because this magnetic field inside the magnet, it will make this charged particle bend this way. And outside the magnetic field is opposite, and it will make the particle bend another way, go another way. And from how much this is bent, we can estimate the energy that that muon had. And also from the way it bends, we can say if it was positively charged or negatively charged. So this is what it looks like when a muon goes through. Then if we have quarks going through, so one thing with the quarks is that the force between them, it's so strong, those gluons that are exchanged, if you remember, that you can never ever have a quark, see a quark on its own. It's always bound together with another quark, either one other or with 3 quarks. So that means what we see is always a bound state of quark called hadrons. That's why this is called a hadron calorimeter. So with everything that's a bound state of quarks, if they're charged, they leave a track in the tracker and they dump all their energy in what's called the hadron calorimeter. And we can measure the energy from how much they deposit of their energy here. So that gives you a way of finding something like the Higgs. So let's say the quarks come in, they ripple the Higgs field, the Higgs is created, and it immediately decays into 2 particles we can see, standard model particles. For instance, it can decay into 2 photons. And it would look something like this in the language of Feynman diagrams, we call it. The Higgs is produced and it decays into 2 photons. then what we would do is we would measure these, we would find these photons in the detector, we would reconstruct them, and we would take their masses, and the mass of these two, if they're made from the Higgs, should be the same mass as the Higgs boson. So we would see it as a little bump around the mass of the Higgs boson over the smoothly falling background. So that's how we find particles at the Large Hadron Collider. We see it often in the mass spectrum. Okay, so if the Higgs decays to photons, I should also show you what it looks like if the photon goes through the CMS detector. The photon has no electric charge whatsoever, so it leaves no little bleeps here in the tracker. It also doesn't get bent by the magnet. We can only see the photon from this energy that it leaves in the electromagnetic calorimeter. Okay, so that's what actually happened in the end. We measured the Higgs boson. We found it in that exact way as a bump on top of a background. And in 2012, we announced that we had discovered the Higgs at the Large Hadron Collider. This is Fabiola, who's now our Director General. She announced the discovery. Both CMS and Atlas saw this bump on top of the background. We had invited Englert and Higgs. Braut was unfortunately dead at that point. And it was an extremely emotional moment. Like, these two men had waited 50 years for this discovery. And so it was extremely exciting. I was also there as a summer student. So I have to say that was really a highlight of my career. It was extremely exciting. So this thing we predicted in 1966, we found in 2012, and that gives you the idea of how much we trust this model and how good it actually is. So this is our quantum fields post 2012. We have the quarks, the leptons, the force carriers, and this really, really special particle called the Higgs boson, giving all the particles their mass, with a mass itself of 125 GeV. And all of these particles and how they talk to each other, how much they talk to each other, how much they talk to the Higgs, it's all written down in something we call the standard model of particle physics. It's a beautiful formula, a small formula that you can see it here on this one slide, which describes how everything in the universe interacts with one another. Almost. So you can kind of say, wow, okay, what now? We waited 50 years, we found the Higgs, we know why particles have their mass. Are we done? Do we have the standard model? Is our picture of the universe now complete? Why should I even bother going to LHC and work for CERN? The questions are all answered. But that's not true. We have a few very, very big problems in particle physics that needs an answer and that we're working hard on providing an answer for. So let's go through them quickly at the last part of the talk. So the problem number one is related to the Higgs boson itself. So we found the Higgs boson. We were extremely happy to find the Higgs boson, and it sort of closed the chapter of the standard model. It made the standard model complete. But the mass of the Higgs boson was really problematic. The mass was 120. Oh, someone else is drawing on my screen. Thank you. So the mass was really, really problematic. And I'll try to explain it simply to you in these few slides. So there are two terms in the standard model that give us a problem with respect to the Higgs mass. It's this term here, and it's this term here. So let's talk about them quickly. So this first term here means the following. It corresponds to this Feynman diagram here on top. So when we physicists try to do calculations in quantum field theory, we use quantum mechanics, and we use something called Feynman diagrams. When we want to calculate the probability of something to occur, we use these diagrams and we do calculations to calculate the probability of a particle moving from X to Y, let's say. So the Feynman diagram for the Higgs to go from one position in space, let's say X, to another position in space called Y, is given by this diagram. And this diagram also tells you that the Higgs has a mass. This diagram says Higgs has a mass, and the probability for the Higgs to go from X to Y is given by this line, which corresponds to this term in the standard model, Lagrangian. That's all well and good. Then we have a second term, which is this one down here. which is how the Higgs talks to itself. So what can happen is that you can have one Higgs at a position W and one Higgs at a position X. And these two Higgses will travel and they will annihilate each other. They will meet and just annihilate, disappear, and make two new Higgs bosons, one that goes out, which goes to Z, and one that goes to Y. So there's all these 4 different Higgs particles. Okay, that's fine, that's good. That's just what these terms mean in quantum field theory, in Feynman diagrams, what we use to calculate probabilities of a particle going from A to B, and also should give us the mass of the particle. Now let's look a little bit closer at this diagram down here with the 2 Higgses coming in and the 2 Higgses going out. You can also imagine this thing happening a little bit differently. So let's say that instead of having 2 Higgses coming in and 2 Higgses going out, you just have 1 Higgs coming in, another Higgs coming in, and then the 1 Higgs that came in just keeps going. It's not annihilated. They just talk to each other a little, and it just keeps going out. So this is the same. Higgs Z, Higgs C. Higgs X, this Higgs disappears and turns into another Higgs. Now, in the language of quantum field theory, you can draw this diagram differently. You can draw it as an arrow from X to Y, which is just this arrow here, with a loop, with something we call a one loop correction. I know it's really, really weird, but this is what we do every day to calculate the probabilities of things happening in quantum field theory. Now there's a problem with this diagram here, and that's a basic rule of quantum mechanics that says if a Feynman diagram has the same starting condition, Hx, and the same ending condition, Hy, they must be included in any calculation. So if you want to calculate the probability of a Higgs going from X to Y and the Higgs having a certain mass, you need to include this probability in your diagram. What this means is that you could say that this diagram gives Higgs some bare mass. That mass needs to be corrected by that diagram. If the probability of the Higgs going from X to Y is given by this, that probability must be adjusted with this diagram that we call a radiative correction. I know this is quite complicated and I wasn't sure if I should talk about it here, but it's quite exciting, so I've tried to make it comprehensible. Okay, so we have this correction. What does it do? Why do we care? So let's say I want to calculate the Higgs mass, the one that I measure in CMS. If I want to calculate that, I have to include this Feynman diagram. This should give you the bare mass, the real mass of the Higgs boson, let's say. Then we have all these other diagrams with loops on them, and they should change the mass a little bit. They can change the mass by 5% up, 10% up. They can make the mass higher. And there's not only Higgses that can go around in this loop. You have to include every loop that has either a fermion going around. So for instance, it can be a top quark that's being emitted and reabsorbed, a W or a C or a Higgs. And all of those are added as corrections. This is problematic because I measure a Higgs mass of 125 GeV in CMS. Then I have this diagram here that has some value. It's not in the standard model, I have to measure it. Then I have all these corrections, radiative corrections, we call them, which are here, which makes the mass change a little bit, get a bit higher or get a bit lower. Now, the problem is because of this loop, this term is huge. The corrections to the mass is huge. So for instance, here you can see the correction to the mass from this top loop, if a top goes around, here if a W or a C goes around, here if a Higgs goes around. So that means we have to set this value of the Higgs mass, this term here, we set it by hand. And in order for that value, this number minus this number to be 125, what we saw, this number needs to be huge. And we don't like that. We have to put by hand in a huge number in our theory, which is not good. That means it's fine-tuned. It's some weird reason, this parameter, we just put it to something really, really big. And that's a problem. So this is something we call the hierarchy problem, and it's one of the biggest, part of being one of the biggest unsolved questions in particle physics. Now, in order to solve problems like this, we've proposed other theories. So you've maybe heard about something called supersymmetry. So supersymmetry is an alternate theory to the standard model of particle physics, and it says, Let's say I have a bunch of standard particles, the up, the down, all those things you saw before. Then there should also exist supersymmetric particles, twin particles of those particles that are opposite, a little bit different than the standard particles. So for instance, all these particles should have the same supersymmetric sibling, and all of these should have the same supersymmetric sibling. Now, these supersymmetric particles have some weird properties. They have some opposite properties than the normal particles, which means that when you calculate the Higgs mass, before you had this loop with a top, you can now have another loop with a stop, a supersymmetric top. And these will cancel each other out, meaning you have no correction to the Higgs mass. So that's supposed to sort of solve this puzzle of the Higgs mass corrections. But if these two were identical, they should also have the same mass. And we haven't seen that yet. And we haven't seen them at even way, way higher masses. So at this point, supersymmetry to me, it's kind of dead. It's not, we're not going to find it, and it's not the real description of the universe. But I wanted to mention it because I think a lot of you have probably heard supersymmetry being discussed or mentioned in your careers if you've been interested in particle physics. Okay, so that's one problem, the Higgs mass. Then we have a huge problem, which is that the standard model does not include gravity at all. So it describes all the forces and all the particles, but the force we feel on a day-to-day basis, the gravitational force, it's not included in this model at all. You can phrase this in a way that we can't find a quantum field theory for gravity. We can't find a particle that describes gravity, and such a particle we can call it a graviton. And this is under severe scrutiny in the field. People are studying quantum gravity, unified theories, all we can to get gravity into the standard model. Another question is we can't explain why gravity is such a weak force. So all the other forces are very, very strong, but the gravitational force in comparison is billions of times weaker than the other forces we have in the universe. And there's nothing we know of that can explain why gravity is so weak. And this is also strange because the force you feel every day is gravity. So it's there, but when you compare it to the other forces, it really is a very weak force. We also have other theories to explain that, why gravity is so weak. And one of those is extra dimensions theories. And in extra dimension theories, we can imagine that there is some hidden world we humans cannot see where gravity lives, and gravity is a really strong force. Then there is some hidden dimension where gravity gets weaker and weaker and weaker. And then when it comes to our world, where we are, our 3 space dimension, 1 time dimension universe, gravity looks as weak because it just got weaker as it diluted through this 5th dimension. So the question here is if we can produce gravitons at LHC and find proof for such extra dimensions theories. So problem 1, Higgs mass. Problem 2, biggest problem in my opinion, gravity. Then we have something called dark matter. And I think that's also something that you've all heard about. So in particle physics, we keep saying we have this great theory of the universe and how particles interact, but we can actually only describe 5% of the matter we see in the universe. From measurements, we've seen that 26% of the universe is dark matter. We can't see it. And the rest of it is some dark energy that we also can't see and we don't know what is. So one of the reasons we think this is the case is because we've measured galaxies. We've seen how far do the stars go around the galaxies. Now, if the galaxies only has the matter we can see with our eyes, we would expect stars further out to go slower and slower and slower. Here you see the speed as a function of distance from the center. They would slow down because there's no gravitational force to keep them at the same speed. But what we see is that the stars further out, they go faster and faster and faster, which means there must be more gravity around them. There must be more matter in the galaxies than what we can see with the bare eye. So at LHC, if there is a matter, if there is a dark matter particle, we should be able to make it in the LHC and we should be able to measure it. So that's also something we're doing now, trying to explain what the rest 95% of our universe is that we currently can't explain. Okay, then there is one also really interesting idea and interesting thought, which is, where is all the antimatter? So I'm guessing you've also heard about antimatter, because there's been the famous Dan Brown book about antimatter, and it's kind of a hyped, mysterious thing. So let me explain you what I mean with where is all the antimatter. So when particles are produced in our universe, they always come in pairs. There's a particle and its antiparticle. So matter and antimatter is always produced together. And they're exactly the same, but they have opposite charges. So for instance, if this is an electron and this is a positron, the antimatter of the electron, it has a different electric charge. This will be attracted to a plus pole, this repulsed. So they're kind of different. And that's what antimatter is. And in the universe, if all antimatter and matter is produced in pairs, you would expect that all this antimatter and matter in the early universe, they would meet and they would just annihilate each other. All the matter and antimatter should be gone if they were identical. But we have a universe of matter. There's you, there's me, there's my computer, there's the LHC, there's the atmosphere, and that's made out of matter. Why wasn't all that matter annihilated in the early universe? There must be something different between matter and antimatter. And at CERN, we're trying to find what the differences are, what can explain why we have matter and we do not have antimatter. Why does the universe exist at all is the big question. So that's a big open question in particle physics. Then finally, there's another problem related to the standard models itself and what it can explain and not, and that's related to neutrinos. So neutrinos are those three particles we saw at the bottom of the table before, and there's those really light particles. I just said they have a mass around 1 eV, but we actually don't know what that mass is. We haven't been able to measure it. It's so light and it interacts almost nothing with us. So it's really hard for us to measure. So every second there are like hundreds of thousands of neutrinos passing through your body. And you don't feel them because they don't interact with almost anything. So what's interesting with these neutrinos is that they come in three flavors. There's an electron neutrino, there's a muon neutrino, and there's a tau neutrino. You can think of the flavors as ice cream if you want, pineapple, pistachio, and strawberry. And these flavors, they can change into each other. This one can become this one. A muon neutrino can become a tau neutrino. And if they can change into each other, that means they must have a mass. If this one can turn into that one, it must have a non-zero mass. So we know it has a mass. And the way we know that they can change into each other is that we can see, for instance, a muon neutrino coming in on this side of the Earth. It goes through the Earth and it changes from being muon neutrino to tau neutrino, muon neutrino to tau neutrino, muon neutrino to tau neutrino. And we measure it as a different neutrino when it comes through. So one of the problems with this is that in the standard model, neutrinos are not allowed to have a mass. It's the same problem as we had before we had the Higgs with the other particles. We cannot explain that they have a mass. We need some extension to the standard model to explain that they have mass at all. So that's a huge open question. And one of the things we could do at LHC is trying to find another type of neutrino that would save this theory. And we call this a sterile neutrino. You can Google it if you're curious what it's all about. Okay, so that's where we stand. So this picture of a complete standard model is not at all true. We don't have a complete standard model. We know it breaks down at some point. We know it can't explain a lot of things. Neutrino masses, gravity, dark matter, the Higgs mass. And that's the reason we're currently working on a lot of new theories of the universe. So for instance, we have M theory, quantum dimensions, supersymmetry, hidden dimensions, composite Higgs, little Higgs. There's so many new different types of theories that we're developing. And we're always trying to test these new theories. So particle physics is not at all a dead field. We have huge open questions that we're trying to solve every day. And one of the reasons I'm talking to you guys today is that I'm hoping that a few of you will think this is really cool and really interesting, and that you'll come help us solve the mysteries of the universe and find the deep underlying explanation between it all.